So in this segment, we'll conclude our discussion of statistical significance, and we'll first tell the history of how this math came about, what is this t-distribution, and we'll discuss some of the terms that you will see when this type of data is presented. So the history of the t-distribution comes from the Guinness Brewery in Dublin, Ireland, back in 1908. And the math at the time, what we know here, this is the fundamental problem, is that when we take samples from a population that's distributed under a Gaussian distribution, these samples do not have a Gaussian distribution. They in fact have what we've already presented to you, a t-distribution, and the key to the distribution is it has fatter tails. It doesn't die off as you go away from the mean. So if this is a normal, the t-distribution has higher probability of having extreme values. If we have lots of samples, which is that concept of degree of freedom we talked about before, T in fact converges to a Gaussian. And the development of the t-distribution is the work of a Guinness brewer, William S. Gossett, who published it under the pseudonym of Student. So this is the t-distribution, and again, as the number of samples goes large, that's effectively this V, we end up with this black curve, and this looks, for all intents and purposes, like a Gaussian. If the number of samples is small, we have this orange curve higher up, and here you can see the tails do not die. There's a lot of likelihood that we have extreme values. And the more of those you have, the less likely it is that you can say something definitive and reject some kind of null hypothesis. So here's the history of this, and this is an excellent article by Dan Kopf on the webpage below. You can look for it up to read more about this. Gossett made his innovations while working as a brewer for Guinness from 1899 to 1937. His primary focus was to maintain the quality of his beer, and that's what Guinness's problem was, while increasing quantity and decreasing cost. And it was during this time that the production level just shot through the roof. They were producing a lot more beer than before, and they couldn't just have somebody taste every single batch to make sure that it was of uniform quality. Between 1887 and 1914, the output of the brewery doubled, and they were reaching about 1 billion pints, which is a huge amount for the era. And Gossett was assigned as part of a team that would answer that question. How do you make sure that the quality of the beer is uniform? So the question that boiled down for him was, what happens in small samples, okay? At the time, methods for extrapolating from a sample relied on having a large sample. So you had more than 30 observations, and you could use a standard normal distribution. Remember, if we look at the distribution that he came up with, as that V becomes larger, you look like a normal distribution. So in many industrial settings, though, it was impossible to get such a large sample. Like you couldn't take 30 out of every batch. You would waste an awful lot of beer. So his goal was to understand just how much representative a sample is when it is small. And the result is this pseudonymously published student t-distribution. The company wouldn't let him publish in his own name, so their competitors wouldn't figure out what was up. So this is fundamentally where statisticians make their money. Given enough data, anybody could probably figure out what to do. But when you have a small amount of data, how do you figure out something interesting to say? How much less representative is a small sample than a large sample, and what are your limitations at that point? And this is what Gossett figured out in his pioneering work. So putting aside the history lesson here, we will need to, a lot of these techniques get used to evaluate things like clinical trials and other things. And as we plan a clinical trial, we use this math, these t-distributions and related concepts, to perform what's called as power analysis. How big a sample do we need to become confident that we can reject our null hypothesis? Remember, null hypothesis means that we have succeeded, and such that our clinical trial is likely to be successful. So given what we know of the population, perhaps from pilot experiments, how big a number of people do we need in our sample such that when we measure something, we can find statistical significance such that we're comfortable saying that we found an effect and that effect is not by chance. So that is a procedure known as power analysis, and we'll discuss this next. So remember again that the goal is to reject the null hypothesis, which means that we have succeeded. We have shown that a drug has some kind of difference. And we start from some pilot experiments, of course, to learn something. The first thing in a power analysis is this thing called alpha, and this is called the significance level. So we're looking for p less than alpha. This is a 0.05 or 0.01. How much are we willing to say, if the probability of seeing this kind of data, given the assumption that there is no difference, what's the threshold below which we say that the hypothesis is false and there's in fact a difference? We have two kinds of error in this type of procedure. The first one is called a type 1 error in statistics, and that says we reject the null hypothesis when there's in fact no effect. This is what's called a false positive, okay? Just like the case of detection, we reject the null hypothesis. We say there's a difference between the drug and the placebo when in fact there is no difference. This is a type 1 error. The second one, and this is the goal of power analysis, is to minimize the type 2 error when we do not reject the null hypothesis when there in fact is an effect. So this is what's called a false negative. Statistical power now, and this is what the root of power analysis is that value assessment is the probability that a test will correctly reject a false null hypothesis. So in our data, in the real world, the drug works, and statistical power is a probability that we will be able to say that the drug worked, given the measurements we're able to obtain. So we want our clinical trials to have high statistical power. So if in fact the drug works, we're going to be able to say that with some confidence. Low statistical power, we have a large risk of committing type 2 errors, of failing to reject the null hypothesis, of failing to be able to say with some confidence that drug worked. And high statistical power, we have a small risk of committing these type 2 errors. So how does one compute statistical power? How do we do this power analysis? And this is the sort of procedure. It's called a power analysis. And here you can see a curve. This is a typical part of this procedure. On the x-axis, we have the difference. This is like the mean minus the mean of the two groups. And on the y-axis, we have statistical power. This is power. Remember, 1 is perfect and 0 is terrible. And we make some assumptions. What is the alpha? 0.05 in this case. What is the standard deviation? This is an estimate of the standard deviations of the groups, and this comes from pilot data. Before you do a clinical trial, you do a small sample, you compute some parameters, and you use it to estimate how big a sample you need. And then what you see with these two curves is if you have, say, 40 people in your sample versus 20 people in your sample. If we make the assumption that the difference between these populations is 5, mean minus mean is 5, you can see that a test with a sample size of 20 has a statistical power of 70%, whereas something with n equals 40 has a power of 95%. What does this mean? Is that if in fact the difference is 5, and this is our hope based on pilot data, and if in fact the standard deviation is 7, and again we get this from pilot data, and if we use alpha of 0.05, there's a significance level. If we repeat this study with a larger sample of 20, we have a 70% chance of finding a result that we like. But if we took 40 people, we have a 95% chance of finding a result that we like. So this tells you that a large sample is better. And if you're going to engage in a large, expensive clinical trial, you want to make sure you recruit enough subjects to have high statistical power. So if in fact there is an effect, you find it, and you don't spend all this money and fail to prove that your drug works just because you didn't recruit enough subjects. So that is the challenge, and this is where power analysis comes from. Of course, you immediately realize that you have to make a lot of assumptions. You have to assume what the difference is, what the standard deviation is. Those often come from pilot studies. You do a small group first to estimate those things and use them to estimate how many subjects you need for a really large study. And this is what's called to properly power a clinical trial. So there are some problems and caveats when we talk about statistical significance and all these procedures, power analysis. The first one is the question that is the null hypothesis justified? Is the probability model correct? So if you say that p is less than 0.05, first we must know p. If p is not really the distribution we assume it is, we're making some erroneous model, then obviously this is not going to be helpful. The second component is that there may be other explanations. So we may say that we have two populations that are only different because the one has a drug, the other has placebo, but there may be other differences. We may fail to randomize a population. We'll see an example in the next segment. The gender balance may be off, the ethnic balance may be off, age may be off, and all those sort of things may be confounds that sort of cause problems for our analysis. And finally, we get into this problem of multiple comparison correction. And in many, to give a short introduction here, and we'll come back to this in week 11, in many scientific studies, in research settings primarily, what happens is that you perform one analysis, you don't find a difference, so you take another measurement from the same people, maybe you do some permutation, you perform another analysis, and if you do enough, eventually you get lucky and you find some analysis that gives you a p-value less than a certain number. Now, the problem is that once you compute 10 analyses, if your original alpha was 0.05, you need to divide that by 10 to be 0.005 if you're going to be honest with yourself, because now you've tested 10 models, so you have to be more stringent. The failure to do this is what's called p-hacking, testing for multiple tests until you find a p-value that you like. This is leading to a huge crisis in social science. We'll come back to this in week 11 of this class. So what does this test tell us, and what does it not tell us? What do we learn from a result of a hypothesis testing, and what do we not learn? What we learn is the probability of seeing this type of data if the null hypothesis is true. What we do not learn is the probability that the null hypothesis is false. And really what we want to learn is whether the null hypothesis is false. How likely is it that our experiment succeeded? The hypothesis testing procedure does not tell us that. All it tells us is the probability of seeing this data if the null hypothesis is true. So there's a common confusion in the field. So this is what a p-value is. A p-value is the probability of seeing this data if the null hypothesis is true. So this concludes our discussion of hypothesis testing. In the next segment, we'll talk about randomization, the other key technique in designing scientific studies and clinical trials. Thank you.